welcome everyone. I hope you're having a good week with all the snow outside. Okay, so what I'm going to do is make a couple of announcements and then get into a new set of topics from today onwards. We're going to focus on text and variations from in the next couple of sessions. Okay, so in terms of logistics, as you know, assignment 2 is due next week, and it involves transfer learning with CNNs and also a problem which looks like a matrix factorization problem, but it's not entirely a matrix factorization problem, but it's supposed to give you a sense of, hey, how do I have a custom loss function or a custom neural network model? Okay. And at this point, while attacking assignment 2, or by looking at example codes in the course URL, what you should be comfortable with at this point is definitely looking at Python code. Much of it is, even if you don't have comments, you can get a sense of what each statement or each operation is doing in a script. And also debugging the scripts that you write. For example, in assignment 1, you wrote some scripts, right? Some, for example, functions, as well as tried out gradient descent and all that. Even with assignment 2, you're writing out for both questions your own solutions. And one very, I guess, intuitive tool that you might have used even before is to use print as a way to debug. Okay, it's an effective, certainly not the best way to debug things, but it's an effective way to debug your scripts. Of course, if you have an IDE that you want to use, then IDE will have things like setting breakpoints and stepping over stepping over each statement one at a time and looking at variables and so on. Okay. For example, VS Code will let you do that with the Python extension. And third, way to debug is to use something called PDB. It's a PDB package has a function called set trace that you can use within Jupyter notebooks. Okay, so set underscore trace function call. If you put it somewhere in your Python script or notebook, in some cell, then when it is executing, the cell will stop at that point, and there'll be a small prompt that will open up where you can type, hey, tell me what's the value of this variable or something like that. Okay, so debugging is something that you will be trying out. It will be kind of important anyway. So you should get comfortable with at least one mode, at least print-based debugging. Okay, so you can print types, you can print the values of variables themselves. You can print if it's a complex object, you can try to find out the structure of the object and so on. Okay, and last thing, which is important, is at this point, just to summarize, that you should be comfortable with looking at Python code, debugging, and also looking at documentation. So you have now had a brush with Keras and TensorFlow earlier in assignment 1. And assignment 2, you've been looking at Torch Vision, data loaders, for example, NN module, and so on, and optimizers, and so on. So there are many different objects that you're trying to use together. So it's good to look at the documentation on pytorch.org or tensorflow.org, whichever tool you're using. Okay, so so that's about announcements. And I guess just to wrap it up, project is intermediate or an initial proposal is due in a couple of weeks. So do talk to your teammates if you have, try to formulate try to formulate problems ASAP if you can, and I certainly ask CTAs or myself if you have any questions.
I guess to add to that, Professor,
any questions
to go off that
by folks at this point?
Yeah. Hello, can you hear me? Hello? No?
Hey, John, we can hear you.
Oh, you can hear me?
I can hear you. Professor, can you hear us?
Okay. I was trying to share my screen, but something's not working well. Okay, let's see.
I think so. He cannot hear us. Something's wrong.
I guess I can just share the screen. Yeah. So where are we today? Today we are at this point. Like as I said, assignment 2 is due in a week, and project intermediate report is due in a couple of weeks. And so we'll start with natural language processing, some topics related to natural language processing, and I'm going to describe what we're going to do in a minute. Next week, we're going to look at a general class of models, which are called sequence-to-sequence models, which certainly can be used for time series as well as text. And text generally has sequential information, so you can use that for text as well. Okay. And after that, we'll look at in the next proper lecture session, we'll look at more modern NLP models, including transformer-based architectures, which have been proposed in the past 3 years, since 2018, fall of 2018. Okay, there's a chat message. Okay, since fall of 2018, and that's what we're going to look at. So basically, these are the 3 lectures at this point, and there's one more project intermediate stuff in between. Okay, let me look at chat. I am not able to hear you guys. Can you hear us?
No. Can you?
Can you hear me now?
I'm not able to hear you. Yeah, now I can hear you.
Okay.
Yeah.
But yeah, when you were asking for questions, I was gonna ask you.
Yeah.
So for the project intermediate report,
yeah,
I was sort of curious what the actual deliverables for that are, because the project section really just talks about the overall goals of the project, like the stuff we have to do by the end of the course. So I guess I was wondering what the intermediate deliverables would be.
Yeah, that is a good question. I think, is it not explicitly stated what the goals are here? Okay. Actually, the intermediate goal is to have a partial snapshot of the same thing. So at this point, you need to have a proposal in the sense of like, what you want to do, what are some candidate models you want to look at, and what aspects of these models you want to look at. For example, if you're focusing on, let's say, text, then you can look at, hey, I have a model which uses something called Word2Vec, and I also want to look at a model which uses, let's say, something else like BERT encodings or something like that. So just an example. Okay, this is just an off-the-fly example. But you need to have it's basically a proposal at this point, the intermediate report. You can also do some preliminary EDA, which just means, hey, this is a text corpus that I'm going to use if you're going to work with text. This is a text corpus I'm going to use, and these are some empirical statistics about this data. Okay. It doesn't have to be text, certainly if you're using time series, like financial time series, you need to get a sense of, hey, these are the number of assets that I'm going to look at, or sorry, the tickers that I'm going to look at, or whatever it is. And this is the time period, and what are the specific problems you're going to look at, what hurdles you may face, and so on. Okay. So if you have some timestamped snapshot of what you want to do and everything, all the things that you've thought about, and also a plan for the next 4 to 6 weeks on how you'll execute it between the team members, then during the one of the lecture sessions, when I'll have a one-on-one meeting with each team, we can debrief and see if something is too ambitious or too simple, or there are some obvious things that I can tell you if I've seen something similar before, or things like that.
All right, that's helpful. Thanks.
Yeah.
Hi, Professor. This is Chaitanya. To add to that note of your project reporting, so should we have like a 1 to 2 pages proposal with like which which neural networks we want to do on the project or technologies we want to do, and a brief description about the data set?
Yeah, I mean, so basically this intermediate report should also potentially, have a huge overlap with the final report. So you should have a good problem statement. Ideal situation is you have the problem statement. It's just that you have not executed it fully. Okay? You've done maybe initial preliminary analysis, preliminary like munging of the data if possible. Yeah.
Okay.
Yeah. Okay, good. So actually, I've shared my full screen. So because I don't know why it's not allowing me to share a window, but that's okay. So let me talk about. Um, okay, let me talk about. Like, yeah. So let me again share my screen. Okay, so yeah. So before I get into what we're going to discuss today, and it's actually related to text and the goals related to that, I wanted to quickly mention something about, yeah. So last time, I think towards the end or somewhere in between, we saw some of these architectures, and the ResNet 18, or I guess in this figure, it's actually some other ResNet, ResNet 28, I guess. So so this is the architecture of this model, which did really well in one of the ImageNet, I guess, image classification tasks, right? So, so this is one example of a non-trivial architecture. We have only seen a very simple con layers followed by pooling layers followed by, let's say, fully connected layers as an example study architecture in the previous sessions. But the architectures that really do well do something extra. For example, this skip connection or a residual connection that you see between, let's say, there's a usual path which has con layers, batch norm, con layers, batch norm, and so on. There's also skip connections. That's called ResNet. And in the first slide of lecture 4, before I start annotating, you can see that there's an example of a slightly different neural network architecture. It's called, I guess, DenseNet, densely connected convolutional networks. It was the best paper in one of the top venues for vision 4 years ago. And if you look at it, it's a architecture very similar to ResNet. Let me zoom into the diagram to get a sense of what is this model, right? So you can think of your tensors as these, collection of matrices. Basically, think of each slice there as a matrix, and then you have a tensor, right? Which is just pack the matrices one on top of the other, and you have a three-dimensional cuboid. And that, for example, at the top left in this figure on the on the right side, is the red colored input, right? Input tensor. And then this particular network called DenseNet, it's basically very similar to CNN. So you have tensor to tensor to tensor to tensor to tensor transformation. So there's a linear path, but there are skip connections, very similar to ResNet. But the skip connections are saying, hey, skip, pass this tensor through a con layer and get the green output, but also pass this red tensor along with the green tensor to 2 layers down. Okay, and again, the red and the green together are also passed 2 layers down to get the, let's say, the yellow tensor and so on. Okay. So what I mean is, if you go from all the way towards the end, let's say the last block here, that block takes as an input not just its previous tensor, but the 2 tensors before, the purple one, 3 tensors before, the green one, and 4 tensors before, the red one. So all those tensors are somehow concatenated or bundled together, and then that whole thing is again undergoes a nonlinear transformation, basically this some layer-wise transformation, and then you get the final, let's say, the last tensor. So this is just I guess, a twist on ResNet. ResNet was only saying, hey, what is the tensor at this point? Take that tensor, do some transformations like convolutional layer and convolutional layer and so on, but also pass the same tensor all the way to the, skip the tensor all the way, 2 steps, and then somehow add them together, and then again do something similar. Okay, this was the ResNet architecture. But DenseNet does something different, and that's why there's dense connections. Like for every you know, every layer, there's like, I look at all the preceding layers, that's a lot of connections. And it seems to do well. And so that's one of the best papers there. Just wanted to quickly mention that before I jump into the objectives for today. Any questions at that point?
Professor, I have a question regarding the RESTnet, but I'll ask after the class because the conversation might go forever.
Yes.
So.
Yeah. So we can use this as a reference. Yeah, definitely. Okay, so what I wanted to do was get into the new set of topics for today. We'll look at, so I guess the title is basically Intro to NLP, and then we'll look at two things. One is, so Intro to NLP, so at least for today's session, the objective is going to be looking at one, I guess, major thing, which is embeddings or vector representations or numerical, I guess, nice enough numerical representations of words, okay, which are, I guess, just called word embeddings. And there's going to be two directions, actually. One is to somehow represent words which are not numbers, right? Which are, first of all, are not numbers. They're just symbols, or I guess collections of characters. And somehow we want to get them into a numeric form, okay? And there are several approaches to do that. And maybe you have already seen some approaches to get some numeric representations of words. But that's going to be the majority of the emphasis for today, in addition to looking at some simpler non-deep learning based text models, starting from naive Bayes and so on. So that's going to be the emphasis today. And then the second direction is going to be how to exploit sequential information in text. Okay, so words in a sentence, in an English sentence, for example, here, have a particular order, right? I can't just jumble the words around, and it'll not have it the same, I guess, semantic meaning, right? So you may not even be able to understand what the sentence would say. So exploiting sequential information is going to be the content of the next lecture. We're going to look at specific models there, but at the end of the day, it's about exploring sequential information. Today, it's about getting representations, or representation just means how do you represent a word in the computer, okay? We don't want to just deal with symbols, and we want to get to vectorial representation, just like we had representations of images as vectors when we had a pre-trained CNN, for example. Okay, those are called embeddings, and we'll look at word embeddings today. And I guess 2 lectures later, just to, 3 lectures later, I might have, okay, I need to update this. But after looking at the 2 directions, which is embeddings and then sequential information, we'll look at the modern class of, I guess, what are called contextual embeddings, which include the famous GPT-3 or BERT and those types of transformer architectures. Okay, and anyway, that's a little bit later. Let's start with the basics now. So for today's session, the objective is to understand how natural language elements, such as words, are processed, at least at the high level. We're going to certainly take a small trajectory through it and look at only a sample of techniques, but it's good to get a sense of how to attack the problem, at least in 1 or 2 ways. Okay. So we look at some simpler methods, as I said, naive Bayes and LDA. Okay. For example, naive Bayes is a mostly a prediction problem, is applicable to prediction problem. But LDA is a tool for unsupervised learning. Okay, so in the sense you don't need class labels and stuff. So it's not for prediction. And then we'll also see, since we saw CNN quite a bit, we can see that CNN can also be used for a specific NLP task. And we'll see that example. In particular, we can do sentence classification, which is exactly the same as, hey, can you find the sentiment of a sentence or a tweet or something like that? They're all the same thing. And we can see that when a CNN can be used there. And then, as I said, the crux of today's objective is to get representations for words. And in there, we'll look at, I guess, what I call static representation. So we'll look at Word2Vec, some details about this, how to get this representation. With that, let me jump over to the annotations. Okay, so yeah, so I just mentioned that. So everybody can see my slide deck, right? Where I can annotate. Okay, so let me open the chat window so that I can see if there are questions. Okay, good. So we'll do it in. So we what we'll do the session in 3 parts. First, we'll get a brief, I guess, a very brief overview of NLP and the variations in tasks and so on. And then we'll talk about the simple models that I mentioned, Naybase and LDA, for example, and include also we'll talk about CNN. It's again a deep learning technique. So we'll talk about CNN-based sentence classification. But as I said, the later half of the session is all about how to get some good representations of words. Okay, and we'll see that these representations of words are just like transfer learning. Once you get representations of words, you can reuse them in many different tasks. As long as there's some compatibility between the tasks that you want to do and the embeddings that you got. So those are the 3 steps. So let's start with the intro to NLP. Yeah. So NLP, or natural language processing, is a very broad field within computer science, which looks at all aspects of natural, I guess, human languages. Okay. So, for example, there are some parts of NLP which look at deciphering ancient text, right, of lost languages, for example. So it really concerns many different areas in pertaining to human languages, and we'll only be looking at a very small set of topics here, and and some of the points that we can notice, even without knowing anything about NLP, is that text is basically a sequence of symbols, at the character level or at the word level, right? So yeah, and so without knowing anything about NLP, if I give you a text and I ask you to try to represent this text in the computer, or on the computer, there are a couple of ways to do it. One is something that everybody knows. So let's say I have a word, let's say we will study, let's say NLP, right? So there are 4 words here. Okay. So I can say, hey, how do I represent these 4 words? One representation that everybody already knows is to consider these words as categorical values. And the moment you think of categorical values, you can say, hey, I can represent, if there are only 4 words in my vocabulary, for simplicity, let's say, then I'll represent each one by a one-hot encoding vector. Okay, one-hot encoded vector, which just means, let me just represent V as 1, 0, 0, will as 0, 1, 0, 0, and then study as 0, 0, 1, 0, and NLP as 0, 0, 0, 1. And if my vocabulary was only 4 words, and if the words, if there was another sentence that had the same set of words, or maybe had the words will and NLP, maybe this was a sentence, it's a malformed sentence, but anyway, so you would just have 0, 1, 0, 0, and 0, 0, 1. Okay, there's one representation, one way to represent these symbols. Okay, this is what I mean by, I guess, these are symbols. I mean, these are not really symbols. I mean, characters could be symbols, but let's think of words also as symbols. Okay. Yeah. So then, okay. But we can also do something very trivial, right? So let's say I can just say, hey, V should be number 1, will should be number 2, study should be number 3, and NLP should be number 4. This is also a numerical representation of symbols, which the computer does understand, right? So instead of so in this case, what I've done is represent the word V with the number 1 right, with the integer 1, and similarly word NLP with the integer 4. Okay, so these are two extremes, right? One is one-hot encoding. Okay, so so here the dimension, the length of the vector, right? This vector should be has 4 coordinates each vector. 4 because the vocabulary size is 4. So one-hot encoding, if you do, you need to have vectors which are at least the same size as the vocabulary size. Okay. On the other extreme, you can just say, hey, I have symbols. Let me map it to another set of symbols, right? Which is, I guess, new symbols. It just happen to be numeric, and the symbols will be just 1, 2, 3, 4. It's just an indexing of these words, for example. Okay, and you'll see that certainly this seems like a bad idea, because why should Bill be assigned number 2? Maybe it can be assigned number 3 or something else. Okay, so there is some issues with this encoding, but the same thing is true for even one-hot encoding, right? So, for example, why should if you look at V and Will or any of the study and NLP, all of them are in this case 4-dimensional, and if you look at there's these I guess representations or encodings that we just chose. So the second, this is like the one hot encoding. This encoding, is not really very useful, in the sense that, for example, if I look at, hey, what's the distance between V and NLP? Okay, some sort of, let's say, Euclidean distance. Euclidean distance is square root 2, right? It's a square root of, subtract those two vectors, you'll get 2 coordinates which are 1 and 1. So square root of 1 square plus 1 square. Okay, but that's true for any pair. So distance between any pair, the first word and the second word, is square root 2. It's the same distance. Okay, so as if the words are, there's no, so 2 words which maybe are similar to each other, their distance is the same as the 2 words which are completely unrelated to each other. Okay? So there are some shortcomings to one-hot encoding as well. In addition to, of course, the encoded vectors being too long, right? They have to be the size of vocabulary, and vocabulary sizes, easily go into tens of thousands or hundreds of thousands. Okay. So anyway, so these are 2 examples that may naturally come to you even before talking about all the details of NLP. All the different ways of representing words. But this is good to have in the back of our mind. And I guess this is a motivation for us to say, hey, are there some better representations of words? And we'll see that at the end of the day, towards the end of this lecture or session, we'll basically be having vector representations of words, very similar to these vectors. Okay, instead of a 4x1 dimensional vector, maybe I'll have a 3x1 dimensional vector. Okay, some vector. And those vectors are just basically called embeddings, and we'll have a clever way to learn those vectors such that, for example, these types of properties like distance between 2 similar words is smaller than distance between 2 dissimilar words. Okay, we can have some properties like that, but we'll get there a little bit later. Okay. So, but since we are talking about intro to NLP, just like for images, although we spent a ton of time just talking about image classification, right? So the CNN architecture, it was at the end of the day, at least what we studied was mostly just doing classification, which is just producing a bunch of scores and 10 class classification, let's say, and you're just classifying. But I think in one of the slides, briefly, I mentioned various sorry, that was wrong. Various tasks, and that include localization. Remember, in localization, you are supposed to, given an image of some object, you need to give a bounding box around it. Okay, and there's also segmentation, where you're essentially, for every pixel, you're saying whether it's of a certain class, a certain type or not. Okay, for example, you have a road. Okay, then you need to say, hey, this is road and this is greenery. Okay, for example. So you need to label every pixel as belonging to, let's say, not road, and every pixel that belongs to road. And similarly, more complex versions of this would be exactly what you would do, for example, in vision-based self-driving solutions. Okay. So there are many tasks in vision with images. Similarly, there are many different tasks with text as well. In fact, I might have a link. Yeah, let me share the link to folks, so that you look at the full bit, full um, set of tasks. Although this link here, which I've shared on the chat, is about a state-of-the-art machine learning for each of the types of tasks, but you can look at the names of the tasks at least there. But we'll talk about some tasks right now. So first example, a first type of task is machine translation. Okay, going from one natural language to another natural language. So for example, I mean, famous examples for this is Google Translate or Yandex Translate, or one of these solutions where you input a sequence of symbols in one language and you get a sequence of symbols in another language, and they are coherent. Okay, they should make sense. And it's actually a deployed in production model. And in fact, this model, I mean, this type of problem, machine translation, is addressed using the techniques that we'll see next lecture, and the more recent architectures that have come up in the past few years. Okay, deep learning architectures. I guess the more one problem that I just remembered, and I haven't listed it here, is search. Okay, so even Google search, let's say, or Bing search and all that. So even search problems have something to do with text, right? You input a query text and you need to get relevant documents. And even there you can have some machine learning models that are based on the types of things that we see today about encodings of words, as well as deep learning driven predictions of which documents are the most relevant to you, and so on. Okay, so anyway, machine translation, one example. Second example is query answering. So here, and these are not, by the way, ideal unanswered problems, okay, unsolved problems. There are partial solutions to all these problems. So for example, with query answering, the objective is to, given a text and a query, respond with a solution to the query, right? So this, at the face of it, looks very difficult for a machine to solve. But a part of the solution to be able to solve this is to really represent words well. Okay, to be able to know, what are entities in the what are the entities being talked about in the text, and which are nouns, which are verbs, which is the root word, and many different things. Okay, and given all that information, you'll be able to answer. I mean, machines are able to answer sometimes the right thing. Okay. Next example is just I guess a wrapper around machine translation, where you can go from speech, right? You can go from let's say English to sorry, you can go from, in this case, I guess, Spanish to English. So here you go from an audio waveform to a text, a sentence which should be correct grammatically, and from that sentence you apply machine translation and go to another sentence, and then do what are called text-to-speech, I guess, transformation. Here it would be called automatic speech recognition. And each of these steps, 1, 2, and 3, they all have an appropriate deep neural network architecture driving these transformations. At the end of the day, these are just functions, right? Functions which take some input and produce some output. Okay, happens to be have some sequential structure here, for example, the audio waveform and the text. But at the end of the day, these are functions. Take some input, take some out, produce some output, and we'll see how, for example, not ASR itself, but we'll see some examples of the sequence to sequence type of models next session. Okay. And I guess one more example here is visual question answering, which is something researchers in academia have been looking at, where the input is an image and a question and a bunch of questions, and you should be able to answer each of these questions. Okay, and for all these problems, it's many of these fall into the realm of supervised learning. So when I said for example, this query answering the underlying model, which takes as input the document query and produces an answer. They have been trained on supervised data sets where there was already a document, there was already a query, and there was already a pristine answer. You had those, for example, that type of data with you, and given that data, you learned a model, which for a new document, a new query can answer. Okay? Many of these things work on the same under supervised learning ideas. But there are many challenging aspects of text with natural language, which is, here are some issues. For example, the sense of the word is unclear. Okay, so for example, if you say, I saw her duck, whether it's a duck belonging to somebody or the person, uh, sat down on the floor is unclear, right? And there's also, of course, a lot of things, here we are just listing out some things related to English. By the way, the link that I just shared, NLP Progress, it also has at least a partial set of problems which have been solved in other languages. So it's good to see some of you who are international can look at them. Idioms, right? So, for example, he kicked the bucket. It not literally taken. There's a literal meaning. There's also a underlying meaning, right? So similarly, reference of what is being referred to is also sometimes ambiguous. Okay, and it's ambiguous even for humans to sometimes understand, but sometimes it's clear to humans, but maybe hard for computers to decipher. Okay, for example, the ball did not fit in the box because it was big or small. So if it's a ball, if it does not fit in the box, it's big, and the box is the one which is small. But you should be able to figure out what it refers to based on which word was used here. Okay. Because if you use big, then it refers to the ball. But if you use small here, then it refers to the box, right? Any questions about this very quick set of at least problems that we saw related to NLP? We'll look at some models which really don't talk about any encoding first, and then motivate how encoding would be useful.
So in terms of this harder text problem, what is it trying to solve here?
I'm just saying that this is a, if you want, so there are same problems, right? So for example, if you want to translate, right? If you want to go back to translation as a canonical example, if you say, I saw her duck as the English sentence, and you want to produce a Spanish sentence, you want to know whether you're talking about the person, kneeling down or, getting closer to the floor, or is it somebody's, actually the animal, right? Or the bird, right? So these are things that computers, it's a priori unclear how machines would get to know this, but I'm just saying that these are some nuances that you'll face depending on your domain or specific problem. Okay. But at the end of the day, as I said, most of the problems that I showed earlier are supervised learning problems. So as long as you have, like for example, translation, you had something similar, or you had idioms for which you had translations from which the machine can understand that when you're saying he kicked the bucket, and let's say you want to summarize, for example, summarization is a problem. By the way, if you look at the nlpprogress.com site, then he kicked the bucket's summary should be something else, right? Depending on how is it interpreted, whether it's literal or whether it's other meaning, right? But you will be, it's not that the machine will figure it out from scratch. You would have supervised learning data where you would have seen some references of kicking the bucket means that person passed away, or maybe it's in the context of obituaries or something. So based on that, the machine would figure out that this probably means something to do with not literally kicking a bucket. So I'm just saying that these are nuances. There's not really problems. I would say maybe issues that one should be careful about. Okay, that may come up if in your specific text problem. Referencing idioms or things specific to certain languages or word sense. I hope that was. I mean, so this actually is just a motivation for saying there are some nuances for text processing that you should be aware of. Yeah. So what we'll do is start with something which doesn't require really embedding the words really well, as in really representing the words really well. Okay, so which I'm just calling as simple representations or models which are simple enough. Here, basically encodings don't matter. Here, in the sense of the set of problems that are going to what the set of example models that we'll see, encodings are not really important. And let's see, the problems we'll look at, the specific models we'll look at. One of the models is called NA-based model. Some of you might have seen this before. The second model is called a Markov language model. The third model is called it's a topic model called Latent Dirichlet Allocation. I'll say what topic model is pretty soon. I think we may not have time for conditional random fields, but we'll look at CNNs because we just did CNNs in the last session. So we'll look at a CNN based. Again, this is a prediction problem, a classification problem. It's a sentence classifier. Okay, these are the example models we'll see, and we'll see that actually up to this point we don't need I guess a so we can get away with, let's say, one-hot encoding or things like that. Even for CNN based sentence classifier, we can get away with one-hot encoding. Okay, so in that sense, these models don't really care about the actual semantic meanings or semantic relationships between words. For example, they don't account for word-word relationships and things like that. Okay. I think it'll become clearer when we look at each of these models. So where is the chat box? Yeah. So first, I'll start with NA-based model, and by the way, this part of the session is just to get warmed up with respect to, hey, these are the different problems, and these are some models that we can pick up and work with. Okay. So the first one is actually for classification. Okay. The first one and the last one, the CNN model and NA-based model, they are for sentence classification. Okay, a sentence or whatever text classification. The second model is not a prediction problem. It's called a language model. It's just trying to, so it's not a, I would say, classification or regression problem. What I mean here is a language model is just supposed to say, hey, what's the next most likely word that should follow the previous words? Okay, for example. So that's what a language model is. Or if you have such a model, you can say this, what's the next most likely word or things like that. So that's this second model. And the model in between, latent dirichlet allocation, is about clustering text. Okay, so if you have a bunch of news articles, you can cluster a bunch of articles to be, hey, these are all sports related, these are all maybe education related, these are all other some other music related, and so on. Okay, of course, if you you can certainly segment a bunch of articles just based on words or some tags or some metadata, but we're going to use the content of the article to do this some sort of clustering in a unsupervised way. Okay, and similarly, as here the last one, I guess the conditional random field, as the name implies, it's a classifier again. It's a little bit more involved, so if we have time, we'll get to it. But otherwise, these should suffice to get a sense of models which don't really account for word-word relationships. Actually, the last one can account for it if we give that as an input, but we'll see. We'll see that how it's going to be agnostic to the word-word relationship aspect. But once we look at these models, then we'll say, hey, let's look at the first non-trivial direction today, which is going to be about word-word relationships and therefore word embeddings, which capture word-word relationships. And next session, we'll look at the sequential nature of text, and not just text, but anything which has sequential nature. How do we handle that? Okay, so representing words is the objective for today. And the next time, it's going to be representing sequential nature of the data, like time series data, or in this case, text. Sentence has a sequential nature. So yeah, with that, let's jump into NA-based. NA-based model is actually I can't rest my hand there. Okay. So the generative model. The generative model just means it just means that all the variables associated with the model are random variables. So what are the variables? So as I said, we want to do classification. So classification has a bunch of input variables, or let's just call it, a bunch of input variables, and let's say we're just doing binary classification. So an output variable. So the output variable, okay. So in this case, let's say yeah, spam, which takes a value, let's say 0 or 1. Okay, it's the name. Let's say the name of the variable is spam, and this variable. Okay, I just gave a word as a variable, but you can just say, and you can call it y if you want. This is going to be a random variable. It's a binary random variable. Okay, RV is just a short form for random variable. And similarly, the input, we're going to say, hey, let me have a, let's say we have a vocabulary size of 1,000. Okay, we only have 1,000 words in our whole dictionary. Then the input is going to be just basically W1 to Wn, and each one of them are just going to be indicator variables. Are just going to be binary, again 0 or 1, of whether the first word is present in the text or not, and whether the first word in the vocabulary is present in the text or not, and whether the last word is present in the vocabulary or not. Sorry, last word of the vocabulary is present in the text or not. Okay, so we only have, so this little n is 1,000. Let's say for vocabulary size is 1,000. So these are all the variables. So this is a variable, this is a variable, this is a variable. These are all random variables. Okay, and that's why I can talk about, hey, what's the probability of this bunch of variables given some other random variables value. In particular, you can see this equation here. There's a key assumption being made in naive-based model, which is saying that, hey, if you give me that random variable, which is the output random variable, if you give me that value, whatever value, maybe it takes 0 or it takes 1, let's say some fixed value. Given that value, the probability of this joint probability of these words, these the first word in the vocabulary being present in the text or not, or whether the last word in the vocabulary being present in the text or not, that joint probability decomposes into individual probabilities. Okay, so the joint probability is equal to the product of the individual probabilities. Okay, so this is called conditional independence, and that's the key assumption in naive-based model. Okay? So once you have, by just saying, hey, this is the assumption, you can actually now say, okay, now let's go back to our original problem, which is the classification problem. If I know which words are present or not in a piece of text, can you tell me what's the probability that this is, what's the probability that spam is equal to 1? Or what's the probability that spam is equal to 0? That's this problem. Right here, I know whether words are present in text or not, right? Because it's conditioned on that event. So given the words, I can tell you what's the probability of spam or not, and that you find. So whether the objective of the classification is just find this, okay? And if probability of spam is equal to 0 or 1, whichever one is the highest, you may say, hey, that's spam or that's not spam, right? Now this probability, because of Bayes' rule, is just going to be equal, or not equal, sorry, proportional. This is a proportionality symbol. It's going to be proportional to the probability of spam times this joint probability. Okay, this joint probability that we got from the previous equation, and that's just for Bayes' rule. So we know that what is Bayes' rule? Probability of A given B is equal to probability of B given A times probability of A divided by probability of B. Or you can say, you can forget about the denominator and say probability of B given A times probability of A. And that's exactly what we wrote, where A happens to be that spam random variable or not. Let's say spam is equal to 0 or spam is equal to 1. And B random variable, so B just happens to correspond to this W1 to Wn random variables. Okay, So, and this is where we use the key assumption where the B, if it's W1 to Wn, that probability of the joint probability of W1 to Wn just decomposes into the probability of W1 times probability of W2 times and so on. That's Bayes rule in, sorry, that's Ney-Bayes model in one slide. Any questions at this point before I jump to the next slides? Also talk about Ney-Bayes model, but I wanted to pause here to see if there are any questions. Okay, so I think, I mean, folks who have seen Ney-Bayes model, for them, this should just be a recap of what they've seen before. So confirming what you've seen before, that's good. So let's now, as I said, because they're random variables, I'm just spending one more second on how people talk about this key assumption, right? So actually, as I said, Ney-Bayes model is a generative model. In fact, there is a it also belongs to the class of what I call graphical models, okay, or what I call Bayesian networks. Is an example of a or a graphical model. Actually, in fact, it will be called a directed graphical model. Okay, and so since I just said, hey, this is an example of a Bayesian network, I just want to show you the graph. So what we said in the previous slide is enough to describe an Ney-Bayes model. But just to kind of further, say that, hey, there's a different point of view. There's not a different point of view. Sorry, it's just a different, I guess. An extra bit of information about Ney-Bayes model is you can represent the random variables as a graph. Okay, and that's why this is called a Bayesian network or a graphical model. And the graph will just have nodes as the random variables themselves. As I said, spam is a random variable, therefore there's a node or a blue dot here, this circular thing here. And similarly, each of the words is a random variable, so each one will have a node corresponding to them. Okay, graphs basically just means a bunch of collection of nodes and edges between them. It'll in fact, the graph is going to be a directed graph, so there's going to be a directed edge from spam to each of the words. Okay, so why is there a directed edge? In fact, this directed edge is what is capturing the conditional independence assumption that we just mentioned. Okay, so if a condition on spam, each of these random variables w1 to w2 to wn are independent of each other. Okay, that's what is key assumption, and this graph somehow captures it, and that's what I wrote here. Okay, this is the assumption. And so the left hand side and the right. So this graph here can be drawn in a little bit more efficient way by saying, hey, I don't want to repeat, each of the other edges. I can put a box around one of the representative random variables and just say, hey, this goes from 1 to n. Okay, this is called a plate notation, but that's not very critical at this point. But it's just a graphical representation of the assumption. Okay, the key assumption is this. And okay, so that's great. Now we've described a model, but how do we fit data to it, right? So the way we fit data. So remember, to classify, we just need probability of this is spam is equal to 0 or 1. Or here, actually, we just say probability of spam is equal to spam or spam. Okay, that's what is there in this slide. But probability of spam is equal to 0 or 1. We know, let's say probability of spam is equal to 0 is proportional to, sorry, I think, let me actually explicitly say this, given text, right? I mean, given text. Spam is equal to 0, given text, which was W1 all the way to Wn, right? We said this is proportional to probability of spam is equal to 0 times probability of W1 is equal to So whatever the W's were, so here W1 is equal to, let's say 0, W2 is something else, W1 is equal to 1, whatever the specific values that the text took, right? So here we'll just say probability of W1 is equal to 0, given spam is equal to 0, times probability of W2 is equal to something, given spam is equal to 0, times all the way to probability of Wn is equal to, in this case, in example 1. So here it's 1, given spam is equal to 0. Okay. So what are the parameters? The parameters are going to be, if I know, so the parameters are going to be all these probabilities. Okay, these are all probabilities that I can learn from data. Okay, by which I mean that at any test point, given any text, there will be some words which will be present in the text, some words will not be present in the text. Okay, at test time. But forget about test time. At training time, I have a table, right? So each text, right? So let's say each sentence corresponds to example. I have a table where word 1 all the way to word n. For example, this is 0 or this is 1, and maybe 0, 1, 0, 1, and so on. And let's say this is spam. So you'll have a table like this. Okay. From this table, you can compute this condition, this probability, marginal probability. You can also compute each of these conditional probabilities. Okay. Once you compute them, then for any given new text data, you can compute what is the probability of the text being spam or not. Okay. And that's exactly what's being mentioned here. So the algorithm is you find how probability of spam is equal to 0 is the number of times spam was 0 in the whole data set. So if my data set has let's say 1,000 examples, 1,000 rows, whatever is the number of columns, then you just find how many times was it ones, how many times was it zeros. Okay, maybe 4 times zeros and 2 times ones, then the probability of spam is equal to 0 is just 4 divided by 6. Okay, that's marginal distribution. I can easily compute 4 divided by 6. Right, probability of spam is equal to 0. So that's this computation here. Similarly, the probability of xi, or actually wi, is equal to true, or true, basically, let's say 1, given spam. You can just find, hey, tell me whichever rows y was equal to 1, which is the spam is equal to 1. In those rows, in how many locations was w equal to 1 or 0? Okay, and based on that, you can just do a count divided by count, and that's going to give you an estimate of the probability of that word being present when spam is equal to 1 or 0. Okay, once you have that, you can just compute, as I said, you can just compute for any new text. You can just multiply these probabilities that you've already computed using training data to get an estimate of whether that text is a spam or not. Any questions at this point? Okay, there are no questions. Then let's move forward. So one thing I do want to point out at this point is we didn't really use any information about words themselves. Okay, so in the sense whether the words, we didn't really care about any meanings of those words, right? We had, let's say, a vocabulary size of whatever, 1,000 or 10,000. Then we were just looking at these random variables w1 to wn as indicators of whether the word's present or not. Okay, that word, and some other word, maybe they are contextually similar. Maybe they, any word-to-word relationship is not really material to this model. Okay, that's what I want to say. Now let's look at the next, example of a simple model. It's called a language model, and it's based on, it's going to be relying on some sort of a Markovian property, but more, I guess, the more important, I guess, the more core of this idea is the following, right? So in particular, we look at a character level model, but we can also have a word level model. Okay, so character level, word level, it just means at the symbol level, whether you're consider the symbol to be just a character, like each alphabet, or you want to consider each symbol as a word itself, it's not important here. Okay, I mean, in the sense that you can apply the same model at any level. So a character level language model is as follows. By the way, language model in general allows you to generate new text. Okay. We'll talk about how to generate new text in a second, but what is this model? Like, how do I use data to learn this model? Okay, let's tackle that problem first. And then once we have a representation of this model, we'll talk about how to generate text. And it's going to be pretty straightforward. So the idea is you pick you pick what is called an order. Let's say 2 or 3 or 4. It just means, so the interpretation here is that only the previous 2 characters, or the previous 2 words, or previous 2 words influence what is the next most likely word. Okay. And for each, so let's say we have a training sequence, since we are talking about character level. So let's say the training sequence is hello. Okay, so HELLO is a sequence of characters that where, for example, the character L should follow E, or it should follow, for example, L, right? So once you have like an example character sequence, then what you do is you just compute the conditional probability. Just compute the conditional probability of the next character given previous 2 characters. Okay. So, for example, the probability of a character L given HE is the number of times you will see the character LHE divided by the number of times you will see character HE. Okay. So this is an example of, this is just trying to say, hey, what's the probability of seeing most likely next character given the previous 2 characters? Okay, and you're just doing a counting among your training, you're just counting among your training sequences, or for example, words, how many times did this happen? And based on that, you can say, hey, what's the most likely character that can come next? Okay, and not just that, what's the next most likely character that can come next? You can also get those numbers, right? Once you have that, you can generate new text by sampling, which means that, for example, I can start with H and say, hey, what's the, let's say I start with 2 characters, HE, and say, what's the most likely next character that should come? You will have a distribution over all the next characters. Okay, maybe 26 next characters that are possible. And from that, you can sample. Let's say it just happens to be L. Okay. And then given these 2, you can say what's the most likely next character that can happen. Maybe it turns out that it's not L, but maybe P. Okay. So so this is how you generate, for example, a new sequence. Okay. So and so on. So you can generate new sequences or new text by sampling. Any questions about Markov model and what a language model subject is to generate new text? It's not just to generate new text, but once you have a language model, you can do a lot more things. But here we're just giving an example of generating text, generating new text.
Professor, is this the model being used while you're using, the texting and all? We get the
yeah.
Okay.
Yeah, that's a good question. So when you use the keypad in your phones, at least previously, this is a very effective model. I mean, this is one of the candidate models. I mean, you can use many choices for doing the same thing. For example, you can even do dictionary lookups, right? You can look up, hey, this is a partial prefix for which words are there in the dictionary, and do something else. But here you can just do in a completely data-driven way. Yeah.
Okay.
Yeah.
Thank you.
So autocomplete, you can use this. But in general, not just Markov-based models, but any language model, autocomplete is a good example for language modeling. And we'll see many other examples next session when we look at not just autocomplete. For example, I think Google Mail has this feature of auto reply, right? You'll literally write the answer for you. Yes. So that's generally a sentence, right? So that also can be done using if you can get a handle on language models.
Apart from English, is there does this model handle other languages too?
Yeah, I mean, so that's a good question. So I guess the short answer is it should, unless the language has a completely different way of constructing, the sequence of symbols. Okay. Generally, most languages will have a particular reason why some symbol follows the next. When I say symbol, just think of word. So there's a reason why a word follows another word. Okay, maybe the the grammar and the way the words follow each other is not the same as English, but there will be some structure and more on models which are, these are all, by the way, data driven. So they should be able to pick up such patterns, okay, whether it's a different language.
So there is no pre-trained model or something for us.
There are. So there are going to be pre-trained models for many languages. In fact, there are pre-trained languages for many different languages provided. But what is this model is the question. Okay. So for example, there are pre-trained models for language, but there are also, we'll look at, for example, one type of pre-trained model today, which is word embeddings. Okay. Once you embed a word, let's say model has a particular vector, okay, and you can use the same vector whether you're talking about model in the context of, let's say, news articles, or whether you're talking about model in the context of, let's say, chapters in a textbook. Okay, so you can reuse the same embedding, for example, same representation. In that sense, you can use pre-trained models. But we'll talk about pre-trained models a little bit more over the next 3 sessions, so it'll be more clear.
That makes things easy. Thank you.
Yeah. So very similar to image-based pre-trained models that, like, for example, ResNet 16, or sorry, ResNet 18 that you have been looking at in assignment 2. There'll be some pre-trained models, whatever models mean, that can be used for text as well. It's just that this idea of transfer learning for text had a huge bump in the past 3 years because of transformer-based architecture. So we'll see, we will look at the narrative in a few sessions, in a couple of sessions.
Okay, Professor. Thank you.
So, Professor, quick question. Now, this we have certain South Indian languages, right? Now, in English, when you start typing T, that translates. So, do you think that is also kind of a part of this? Because if
so language models are specific to, so you can have a language model for any language. In fact, but we need training data. So by the way, this getting a language model using Markovian idea is a very straightforward idea and doesn't need any labeling or anything. In fact, one of the big strengths of learning a language model is you don't need any annotation effort, because literally if you just get a good clean corpus of a language, you'll have that sentence structure and so on. So you will know what's the next likely word given the previous word, or what's the next likely character given the previous few characters, and so on. So you can have language-specific language models, and there are quite a few. By the way, just to give you some information, assignment 3 will have language-to-language translation. So you can pick your favorite language if you want to translate English to that or something like that. Okay. So next, let's talk about another unsupervised problem. It's called Latent Dirichlet Allocation. Okay, so LDA is the name of the model. Okay, it's going to be about classifying a corpus of news articles, classifying a corpus of tweets, whatever it is. You can do that. And then, not classifying, clustering a corpus of tweets, or clustering a corpus of articles, or documents, 10Ks, CC filings, and all that stuff. We'll look at the model. But before looking at the model, I just want to tell you a little bit about a specific type of distribution, very similar to, we have seen some distributions before, right? For example, you have seen the normal distribution. And you have seen many others, right? One of the types of distribution, named distribution, is called a Dirichlet distribution. Okay. So a Dirichlet distribution. So I want to first mention this and then talk about LDA, because Dirichlet distribution is going to be part of defining the model. So I want to first tackle Dirichlet distribution, what is it, and then talk about LDA. So if you think of normal distribution, let's say normal distribution 2 dimensions, right? So just to set the same type of stage, if you look at the top view of a normal distribution, let's say it's x1 axis and this is x2 axis. If you look at from the top, a normal distribution, for example, it'll have concentric circles like this. Okay, for example, let's say mean 0, 0,0. Okay, just means it's like a bell-shaped curve from the top. Okay, from the sides you can literally look at like a bell from any side. So this is how it would look like. So I hope folks are, like in one dimension, it will look like this, but in 2 dimension, you can imagine a bell, right? An inverted bell. And if you look at it from any side, it's literally going to look like a bell. But from the top, it's going to be like a contour plot. This is called a contour plot, by the way. It looked like a bunch of concentric ellipses, okay, in general, or concentric, I guess, even circles if the distribution is symmetric. So it's a normal distribution. It's a distribution over the entire 2D plane, right? So normal distribution, if you think of a normal distribution in 2D in 2 dimensions, the coordinates can take any values, right? Because the support, there's a probability of, sorry, not probability. If you sample from this normal distribution, let's say from 0, 0, and let's say the covariance matrix is 1, 0, 0, 1 for simplicity. If you draw samples, you can get any numbers. Okay, you can get minus 100, comma 200, for example. Like you can get a 2-dimensional vector or something like this. So I'm just saying that the support of support in the sense that what are the possible values that the random vector in this case can realize? It can be any 2 numbers, right? In the first and the second coordinate. Similarly, a Dirichlet distribution is a distribution over a limited part of the 2D plane. Okay? So here in this bunch of 6 figures, we're just showing how the Dirichlet distribution looks like on the part of the 2D plane. In particular, the part of the 2D plane is this triangle. Okay? This triangle. Okay, so just think of this 2D plane as, I'm just gonna, I hope people can visualize. So think of this 2D plane, 3-dimensional space, where I say, hey, just look at the look at 3-dimensional space, but look at a plane which is not parallel to any 3 canonical planes. It's basically has intersection 0, 1, 0, 1, 0, 0, and 0, 0, 1. Let's say so. This is x, this is y, and this is z. Okay. So think of a plane which is like a little bit tilted, right? But cutting through these 3 points. Okay, this is going to be a plane like that, and then further, I'm going to only take a part of that plane. Okay, it's just going to be this segment of that plane. Okay, this segment is called the simplex. It's just a name for it, but that doesn't matter. So all these figures you see, there's some triangular yellow region, right? That is that segment. Okay? It's just a 2D plane, and it's being shown in 3 dimensions because you know in reality it's supposed to have that, it's supposed to be intersecting the three axes like this. But of course, if you flatten it, it's just going to look like a triangle, right? It's going to look like a triangle. Okay? If you flatten it, I mean, if you look at the top view, it's going to be looking at a triangle. Here they did not look at it, they did not flatten it, so that's why they have drawn a 3D figure. Now the distribution is just a distribution over points in this triangle. Okay, in this triangle, this is a closed area, and you can think of a distribution which is not extending. Normal distribution goes all the way from minus infinity, for example, in 1 dimension. Think of it as like restricted, like any. So for example, here you can see, the distribution is restricted. In fact, the distribution is getting a peak for some value here, and for majority of the points here, it's almost 0. Okay, and certainly 0 for anything outside for sure. Okay. Similarly, here you can see that it's 0. The distribution, the probability value density function is close to 0 here, whereas somewhere over here it's fine. Okay. And you can have different types of distributions. It can have different centers. Center is here, this guy's center is here, and so on. Okay. That's all it is. A Dirichlet distribution is a distribution over this limited space, limited, I guess, doesn't have to be a 2D plane, but in this illustration, we're talking about a 2D plane. Okay. Any questions about just understanding, getting a Dirichlet distribution in on simplex? So think of a normal distribution. Just say, hey, you cannot take values. If you want to look at a distribution, as I said, normal distribution can be anywhere on the plane, like huge. Think of this as like minus 100 and all that stuff. Instead of that, a Dirichlet distribution can only be on some sort of a let me not put axis values there. Yeah, This distribution can only be on like some sort of a triangular area. Okay, so only this area can have a probability value. Everywhere else it's 0. Whereas normal distribution can have value everywhere. Okay. Now on this, maybe there's some higher probability masses here, maybe less probability masses here, and less probability masses here, and so on. So that's a digital distribution, but doesn't have to be 2 dimensions. Okay, so the whatever I've said so far can actually be extended to more than 2 dimensions or 3 dimensions or 4 dimensions. Okay. So what's the special about this? What's the special about this triangular region? Okay, there's one really nice property about this triangular region, and that is every point in this triangular region, okay, it's since it's a point in three dimensions, right? So each of these triangular region, each of these points, belongs to that plane, and that plane is in 3 dimensions. So certainly it'll have 3 coordinates, that point. If you sum up the values of those coordinates, it will sum to 1. Okay? Sum of coordinates, let's say x1, okay, let's write I is equal to 1, 2, 3 is equal to 1. It will sum to 1, and xi will also be greater than or equal to 0. And that you can see, right? It's clearly, for example, here in the bottom left side, you can see that, let's say, the corner points 0, 1, 0, certainly they sum to 1, and they're all positive, non-negative. On the corner points, you can clearly see that sum to 1 and non-negative each coordinate. And similarly, every point on the triangular segment of the plane, every point also sums to 1 and has non-negative values. Okay, it's just like on the positive orthant. If you think of a 3-dimensional view, all these points lie on that small triangular region, for example, in 3 dimensions, which is in the positive side of the positive orthant. Okay, so and that's nice because this exactly corresponds to the definition of a probability mass function, right? If I have a probability mass function with 3 values, then the probability mass function satisfies this property that the sum of the probability mass functions, like PMF, if it's on 3 values, then the value 1 plus value 2 plus value 3 should sum to 1. That's the definition of probability mass function. And of course, the probability mass values should themselves should be non-negative. Okay. So in that sense, if you draw a sample from the Dirichlet distribution, that sample is actually a probability mass function. So if I draw a sample from any of these, from any of these guys, from this triangular area, according to the Dirichlet distribution, just happens to be a probability mass function. Okay. So that's all we need to know. I mean, there are a lot of details, I mean, mathematical symbols and all that to know more about the Dirichlet distribution. But for us, the key idea from this slide is that, hey, there's a distribution over a part of a certain, let's say, 3D space, for example. And the distribution, when you draw a sample from the distribution function, okay, you just get if it's a 3D space, you get a 3-dimensional vector. It's just that the vector corresponds to a probability mass function. If it's 10 dimensions, I'll get a 10-dimensional vector, but the 10-dimensional vector, the coordinates are all non-zero. Sorry, the coordinates are non-negative, and they sum to 1. Okay, so it's all whenever I sample from a Dirichlet distribution, I get a vector which always corresponds to a probability mass function. Okay, that's all we need to know from this slide. With that introduction, let's talk about latent Dirichlet allocation. Okay, so some keywords: latent Dirichlet allocation. So we looked at Dirichlet. Okay, so there's going to be some Dirichlet distribution involved in this model definition, and that's why we discussed the Dirichlet distribution first. We'll talk about latent in a second. So let me first explain what what are the what does the data the data is. Okay, and then how does Dirichlet distribution, how is the data model, and then I'll talk about why the word latent. Okay, so as the slide says, topic models are tools for exploring large data sets, large text data sets. Okay, and you can make some conclusions. Make inferences means just do EDA. Okay, EDA work on the content of documents. Okay, so the content of documents is generally words, and you can you can get some sense of, hey, if I have 1,000 documents, hey, 500 of these documents, certain type of information going on with them. It's all related to and there are some other topics related to sports and so on. Okay, so you can make sense out of it in an unsupervised way. And once you can make sense of it, you can actually, this actually helps, because if you there are many specific problems in NLP. Again, check the NLP progress link over there to get a sense of the types of problems. Summarization, classification, information retrieval, which is what search does. Search is about information retrieval, where you send a query, you get back a bunch of documents. So all those can be improved if you can get, in an unsupervised way, a sense of how do documents cluster together. So for example, if you have a new document, let's say it has a bunch of words, W1 to WN, then you can actually say what is the document about, in the sense that document is going to be about, you may not have specific words like this, weather, finance, sports, but you can say, hey, the document is about 50% of the first cluster, 49% of the second cluster, 1% third cluster. Some sort of a sense of how does this document relate to all the previous documents that we have seen. Okay, so from previous documents, some training data, there's no labels here. From training data, you are unsupervised. In an unsupervised way, you get a sense of, hey, these bunch of documents are similar. Let's call them the first cluster and so on. It's not, cluster is a very informal word I'm using here, but just a sense of, how, what's the, I guess, topic type. Okay, topic is just a name for each cluster. For example, if a cluster of documents are all about weather and weather related words, you can literally call them, hey, the topic of this cluster seems to be weather, dominated, for example, weather word dominated or weather topic dominated. So that's what you can, these types of uh, um, inference that you can draw. Okay, so given a new document, what is its composition, for example? And for this, you actually don't need word-to-word relationships again. Okay, so again, you don't need a notion of embeddings or how word cat and word dog are related to each other compared to cat versus, let's say, house and so on. So you don't need to know that. So let's see what the model is. Okay, I just mentioned what the things are. There's going to be documents. There's going to be articles. Okay, not articles, but documents, which are a bunch of articles. And there's going to be the notion of topics. Okay, topics are just related words. Okay, and we'll see how we can get to um, relation between documents and topics is in the next slide. Um, so here's the idea. So this is also a model. Which means the way to think about this model is, hey, if I wanted to generate a new document, how would I do it? Okay? So any generative model, by the way, whether it's for a specific prediction problem, for example, naive, you would say, how do I generate a new or a new um, uh, document in this case? Okay, so those are the questions that answer generative models, which discriminative models, for example, SVMs and all those types of models, they cannot really tell you. Okay, so because it's a generative model, we're going to talk about can we generate an example document. Okay, if we had parameters. Okay, now we're also going to talk about what parameters and how, and in conjunction we'll talk about how to generate a document. Okay, so what we do document is as follows. We build the topic distribution of this document. Okay, which just means that let's say we have a bunch of parameters, some capital T. Okay, why capital T? Because we'll say that we'll have T number of topics. Okay, and so we'll sample a vector given this parameter. So let's say we have 3x. Okay, capital T is 3. Then it turns out that Dirichlet, whatever parameter alpha 1, 2, 3, is going to generate a 3-dimensional vector. So theta is going to be 3-dimensional. It's actually going to be a probability mass function, and that's what I mentioned ago, right? Theta is going to be a probability mass function such that theta 1 plus theta 2 plus theta 3 is equal to 1, and theta 1 and theta 2 and theta 3, all of them are non-negative. Okay, so first I'll generate this called theta, and given theta, what I can do is I'm going to first assume, I'm also going to assume that my document will have exactly capital N words. Okay, So maybe 200 words. Okay, so I'll prefix that it has to have 200 words. Then what I'll do is for each, so I have to have 200 words. So think of putting blanks there first. Okay, I'll have 200 such blanks. What I'll do is, because I know theta, what I'm going to do is I'm going to use theta to say, hey, which topic would each of this 200 words correspond to? So first I'll say, hey, first word, which topic would it be? Because theta is a distribution of our topics, the three topics, right? In this running example, I'll say, hey, first word maybe is related to topic 1. Okay, so that will say z1 is equal to 1. Okay, and similarly, the second word is going to be z2 is equal to, let's say, topic is equal to 3. Okay, and so on. So I'll assign z3 is equal to 1 and so on. So all the way to z200 is equal to 2. Okay, so I'm going to assign topics to the blanks without filling in the words first. Okay, that's that's step 2. And then I'm gonna say, hey, now I know the topics for each of the blanks, but I don't know the words themselves to finally get the document. Once I fill in the words, I have a document. Okay, and the document will have no sequential information because there is no. It's not gonna have proper. It's gonna have mangled words. Okay, but that's okay. So model that. The way I'm gonna fill in words is that I'm gonna say, hey, if the first blank is for topic 1, what I'm gonna do is go back and look up a probability mass function over the topic 1. So which means that now I need to have an extra thing, which is called a distribution over words for each topic. So if I have 3 topics, and if my vocabulary size is whatever 2000 words, then I'll have a distribution, a probability mass function over these 2000 words, okay, for each of the 3 topics. So I'll have basically 3 probability mass functions. Each probability mass function is a distribution over 2000 words. So I'm gonna say, hey, first word is supposed to be topic 1. Let me go to the first distribution probability mass function and sample a word, whatever that word happens to be. That's the word I'm going to put it in the blank over there, right over here. And now I'm going to move to the second location. Second location topic happens to be 3. Let me go to the third probability mass function, draw a sample from that topic distribution. The distribution of words for that third topic. And whatever word comes up, I'll fill in the second blank and so on. Okay, I'm going to do this in a sequential way. And that's once I do that, I have this collection of 200 blanks where I filled in words. Okay, and that thing is considered a document in this model, at least in this model. Okay? So of course, there's no relationship between the first word, second word, and third word, and so on. The only relationship is that these words happen to belong to potentially different topics, and those topics were pre-selected before the words were filled. Okay. So that's how you generate a document in this model. So in the sense, this model is not really considering any sequential information. And that's exactly what we'll capture next time when we talk about sequential information, next time in the next session. And the second thing is this model also doesn't capture any word-specific or word-to-word relationship. Okay. So, and that, it's clear that there's no like relationship between word 1 and word 2 and word 3, word 4, and so on.
Professor, I have a question.
Yeah.
So here you're actually looking up which topic it is and going to the distribution and picking a word. So is the word which you're picking, is that random or how does it work?
Yeah. So whenever you see notations like this, right? So here or here, the WI is the word I'm going to pick given the topic. That given topic is ZI, happens to be 1 or 2 or 3. And tilde just means, you're drawing a sample from that topic specific distribution or words. Okay, B subscript ZI. So sorry, beta subscript ZI is basically beta 1, beta 2, or beta 3, because ZI happens to take value Z, any of the Z's will take value 1 or 2 or 3, right? Yeah.
Okay. Yeah. And can you please explain the first equation of theta, tilde?
Yeah, theta is again also drawn from the Dirichlet distribution. Oh, this equation here?
No, the above one.
Yeah, the one that, this first step, right? So first step is to draw a topic distribution from the Dirichlet distribution. So this Dirichlet distribution is exactly this. Okay, so in 3 dimensions, exactly what I was saying here. You draw a sample, and that sample, here I'm representing it as x. You can call it theta here. Yeah, and thetas just have to be probability mass functions.
Okay.
Okay. Theta has to just satisfy the PMF definition. Yeah.
Okay. And what is the alpha over there, Professor?
Alpha happens to be the parameter of the Dirichlet distribution. I did not spend time on that. It's basically, hey, for example, this distribution here, you can see that there's a peak, for some values of thetas, right? Values that can be taken, and for majority of the places, it's you can see the plane itself. So maybe the probabilities there are 0 compared to, for example, here. So alpha just controls that. Okay. For example, for normal distribution, you know that if the covariance is very high, then you'll have a certain distribution. It'll look like a certain distribution. And the covariance has some large numbers, and it'll look like a little bit different distribution, right? So it'll become flat or very pointy, something like that. So alpha just controls a distribution. How does it look like?
Okay, got it. Thank you.
So that's a great question. So I mean, folks are seeing LDA, for the first time. This may look like a pretty complicated model. It was introduced about 20 years ago or 19 years ago, 2003, I think. And so the parameter of the model actually just is alphas and these probability mass functions. Okay, because once I know alphas and these probability mass functions, which are betas, then given alpha, I can draw a theta. Given theta, I can specify what's the topic for each word. And given the topic for each word, I can use betas to say which word should be in that location, right? So alphas and betas are what we want to learn from data. Okay? Once we learn alphas and betas, we can say, okay, once we have learned alphas and betas, we can say what the topic composition of any article is. Okay, and we're not going to get into those details, but I'm just saying that alphas and betas are the parameters of this model. Yeah, as I said, betas are the topics, a fixed collection of distribution of words, and those are therefore they are parameters of the model. Okay, so yeah, I mean, if you want to really see what betas would be, let's say, for example, this could be beta 1, this could be beta 2, and this could be beta 3. Okay, so because there are 3 topics, let's say there are 3 betas, all they are just, what does beta represent is basically for each word, it just says what's the probability of that word. Okay, for each word, it says in this topic, the probability of, let's say, politics, president, whatever these things are high. Maybe for other words, it's all zeros, for example. And similarly, if it's a beta 3 topic, then for sports, baseball, soccer, and so on, it's high. And for maybe all other words, including politics, for example, it's 0 and so on. That's what these betas are. And you need to learn them from data. Okay, similar to learning alphas as well. How do we learn that? That's completely, I think we're gonna not talk about it because it's basically related to maximum likelihood estimation and things like that. Some of you might have seen it in 575. If not, don't worry about it. There is a way to go from data, by which I mean things like these documents, to good choices for alphas and betas, whatever they are. Okay, if there are 3 topics, then we'll get the 3 topics vectors, these numbers basically. And the words corresponding to it. I mean, words we already know because vocab size is vocab. Vocab is vocab. Similarly, alphas as well. Okay. And once you have alphas and betas, you can answer for a new text document what is, which type of topic it'll have, or maybe it has one of the topics and some composition of other topics, for example. Let me not repeat this picture, but this picture is basically saying exactly what we just discussed. So let me skip that. Yeah, and this is just a recap. So this slide is just a recap of what we just discussed. Okay, in the again, LDA also happens to be a graphical model. I think I just mentioned graphical model a few slides ago when I was talking about Naive's model. By the way, graphical models are a huge class of models that are very interpretable, but happen to lose out with respect to deep learning in terms of prediction performance and stuff, but are very good for encoding prior information. So if you have an applied problem where you really want to capture, there's a lot of domain knowledge, you want to capture relationship between variables, graphical models are something that to look at. I used to teach that as part of this course, but I dropped it to focus more on deep learning. Um, so here's just a recap. Okay, so the way how variables are related is alphas are outside this box, so they are not random variables. So sorry, yeah, they're not random variables anyway. Let me just put squares around them maybe just to say that they're not random variables. They have parameters basically. Given alphas, you can get this random variable theta for each document. Okay, little d represents document 1 to document d and so on. For each document, once you get that, each document will have capital N number of blanks, and for each blank, you can figure out what is the topic, what's the topic for each of the blanks. Once you know the topic for each of the blanks, given z and beta, you can figure out what's the word in each of the blanks. Okay, and the words you can reorder the words, and it's all the same thing. Okay, and so this is just a summary of that LDA model. Um, and it's also called a plate notation, just so that we have so many variables, we don't have to make many different nodes for each of those random variables. You can just collapse them. It's some efficient notation. If you want to quickly know what LDA is, this is a nice way to quickly remember what it is. Let me not talk about the next slide. So,
Professor?
Yeah.
Before you go to CNN, I have a question. So for LDA, what is the actual use of LDA model? Where do we use it? Like now, as you described, the first word and second word, they don't have a connection, or they're not like predicting based on the first word. We are not filling the second word. It's like random sampling and random generating based on topic. So where do we actually use this?
So it's a tool for unsupervised, essentially clustering. Okay, so if you have seen, okay, let me go back here. Oh, let me go back here. Okay. It's all about clustering, right? So clustering is an unsupervised activity. Similarly, topic models are a type. I would classify them as a type of clustering model. Of course, it's a generative model, so there's a lot of assumptions on the distribution. There's a lot of distributions and random variables involved. But at the end of the day, given a corpus of documents, you can actually cluster them. Okay, once you learn the alpha beta parameters, those are not the final outputs. The final output is for each document, you can say, hey, this document has a dominant topic being politics, and maybe, hey, this other document has a dominant topic being sports, for example. Okay. And once you have, so now what you did is for each document, you in an unsupervised way figured out, for example, hey, this document, so maybe in the training data, you figured out, hey, this document has 0.50 weather type of topics, 0.49 finance type of topics, and 0.01 sports type of topics. These are like extra attributes that you add to your document. Like if you think of like it's just a bunch of text, right? Instead of the document, you can say, hey, instead of the document 1, I can represent it as a feature vector where I can say whether, like I can have topic 1, topic 2, topic 3, and I can say topic 1 has 0.50 representation here, topic 2 has 0.49 representation here, and topic 3 has 0.1 representation. So you can actually create basically features for your document if you want to use it for, let's say, post processing, in the sense of if you want to use it for the classification and so on. But it's just a clustering technique. Remember, even for clustering, if you just do clustering, you can always do classification, right? And that's the whole idea behind KNNs even. Okay, if you can cluster your data, then you can say, hey, any new point, which cluster does it belong to? And you can say, hey, this is a label, for example. Yeah. So wherever you can think of clustering, the same thing you can do with text data. Okay. In fact, for text data, you don't really have a sense of clustering tool right now, right? So you already knew clustering for numerical data up to this point at least.
Yes.
Right. So yeah, whenever you think of clustering, you can say, hey, one of the tools that we can use is LDA.
Okay. Thank you.
Yeah, so actually, let's take a break for 10 minutes. And after that, now we'll talk about all deep learning, so including CNN-based models first. And then, of course, as I said, the crux of the lecture or session today is all about encoding. First slide, I said, hey, encoding could be just one-dimensional numbers, integers, or it could be one-hot encoding numbers. Instead of that, we'll talk about better encodings. Okay, so let's resume at 7:52. Yeah. Okay, welcome back. So before we switch topics, I just wanted to show you a couple of resources that are available from the course lecture details notebook. So it has, for example, a link to this LDA. So you can get a sense of how does LDA work and what are some high level details and so on. Okay. And this, as I said, it's about 18 years old now. The technique. And if you want to get your hands dirty, there's a really nice package that you can use called Jensen. In fact, the subtitle is Topic Modeling for Humans. So you can actually look at various usage of LDA and like, how is it used. And in fact, you'll see that there's actually also some other names, if you can see uh, on the left side here. Word2Vec is what we're going to talk about pretty soon, right after the CNN model. Okay, so Word2Vec, Doc2Vec, FastText. These are all, by the way, somebody asked about pre-trained models. These are all pre-trained embeddings that you can use for things. Okay, so you can do similarity queries. You can do basically search, right, in a good way. So this is a great resource, and we'll probably actually see one example of using this package and t-SNE that we saw last time to visualize these embeddings. Okay, we saw the visualization of the image embeddings, MNIST embeddings in an example notebook last time. So we'll look at visualizing the word embeddings this time. So there is some comments on chat. Let's see. Where is the chat box? Good question. Okay, so there is some questions here. I'll link to the post. This LDA link, it's available on the lecture details notebook, but I can just post it here. And you can, and you will see one notebook that I will be talking about maybe towards the end. But for LDA itself, this is an example of how to run LDA in Python. And the example of about Word2Vec, don't want to show it now. One last thing I want to talk about before I jump to annotation is there's another really nice natural language processing package called Spacy. Okay, that's also a link that I posted in the chat. So Spacy is also helps you do a lot of natural language processing tasks in a very quick way. Okay, so for example, here's a very quick small example that you can do. Actually, what happens when I hit run? Oh wow, it's launching Docker container and all that. Okay, so you can import Spacy and you can say load what is called a tokenizer, tagger, parser, and name entity recognition, I guess object, and so it's basically loading a model, not really a model, but different components of data processing workflow for text, and then the raw text is a bunch of sentences like this. Um, uh, yeah, bunch of sentences like this, and then uh, when you apply this bunch of pre-processing, there are pre-processing steps and also some models being applied on the text, you get an object called doc, and then you can get, hey, in this doc, get me all the nouns and let me just print out all the nouns. Okay, or from this doc, look at every token or basically every word roughly in this doc, and if the doc, if that word is supposed to be verb, by the way. And how do we get this? This operation NLP already gives a certain representation of this text such that you can get the words, nouns, sorry, the verbs, nouns, and everything, and even which ones are entities, for example, and all that. Okay, so for example, doc dot entities has what is the text and what is its label. So you can see that I just ran it, and you can also try it locally on your browser. You can see that, for example, 2007 is a date. American, I don't know what NORP is, North American region, maybe, I don't know. So recode let's say it's a person, earlier this week is referring to a date and so on. Okay, and you can see what verbs are and what nouns are. So really good package to try out. What we'll be talking about today, and we saw with that with GenSim as well, is this. Okay, just one of these bullet points among these many different things that you can do with NLP and in this package in particular. We're going to look at word vectors. Okay. Is there anything else that we look at? Of course, we have done, we have looked at PyTorch and TensorFlow before, and so there are many features here. Certainly have a look at it, and we'll look at transformers a couple of lectures later. Okay, so there are some things among all this, tools and techniques related to natural language processing that we look at, and there's a great package to try out and experiment with. With that, let me go back to annotation. And the annotation is related to this really nice paper from 2014. Okay, so 14 because it says 14 here. So this is a paper from 2014, fall 2014, which is saying how to use TNNs for sentence classification. And the text and what we're going to see today in the next five minutes or so is basically from this paper. Okay, it's called Convolutional Neural Networks for Sentence Classification. And I'm also linking that here, but it's also there on the course page. Okay, course page, go to lecture details, and if you look at the details for this today's lecture, you have this link. And yeah, with that, let me switch over to my annotation thing. Any questions at this point? Okay. Anybody have any questions? Okay, so if not, certainly stay back if some questions come up later, or you can certainly use the chat box to even ask about questions from the first half and so on. We can always pause and take a detour and discuss what we discussed in the first session, for example. So what I'm going to talk about today, what I'm going to talk about now, before we talk about word encodings, is a model which is based on something that we already saw, okay, which is CNN. So in particular, what we're going to do is there's going to be certainly a twist, right? Because sentences are not images. So there's going to be some adaptation that's needed. And once we do that adaptation, you will see that there's a really nice model that comes out, okay? And what this CNN-based model does exploit, okay, as I was saying, there are two things, right? One is encoding the words, these symbols properly, the symbols of natural language properly. Second thing is take sequence info into account. So you'll see that the CNN-based model does satisfy both these in some sense, although it can use any encoding. So it's not really related to encoding in the sense that I can use one-hot encoding as a part of this model, as a part of this training this model. So encoding itself is not being addressed by this model, but it does take sequence into account. Okay, so this is definitely being addressed. Encoding, you can actually give better and better encodings, and that's going to be just part of you picking an encoding has nothing to do with the rest of the model definition. Okay, so we have to pick an encoding as in external to the definition of the CNN model. Okay, so taking sequence information into account is interesting. So let's talk about a couple of baselines first. The baselines are like some just quickly naive models for doing sentence classification. Okay, if we have a sentence, we can just ignore the sequence first of all. Okay, we can ignore all semantic information, and then just think of the sentence as given a sentence, I can just this is what we did for a spam classification, for example. The naive-based models, for example, is that whatever is the vocab size, we're just going to create that vocab size length vector where we'll have a one-hot encoding of, hey, if the word ignore is somewhere, then ignore's coordinate should have value 1, and other places should be 0, and so on. So that's basically bag of words representation. Okay, bag of words. And you might have seen this bag of words as a phrase elsewhere. So it just refers to ignoring the sequential information and then just saying, hey, whatever words are present, just have an indicator variable corresponding to them, and whatever words are not present have a 0 value corresponding to them. Okay? So that's a fixed size, fixed length, because that's typically going to be the length of the vocabulary size. Okay, and then you have fixed size input, therefore, which is length of vocabulary. Sorry, length of the vocabulary, yeah, which is the same as the size of the vocabulary. Sorry, and the output is whatever classification. So that's fine. So this is one idea you can think of. Again, certainly it doesn't use any information about the words or the word relationships and all that. The second example, or second, I guess, model that we can think of is that if we had word vectors or word embeddings, if we had it, okay, if we had encodings or embeddings or whatever, so if we had them, then we can take a weighted average or just the average of these word vectors across a sentence. Let's say the sentence has 5 words. Then each of the words will have a vector. I can just pick, maybe, generally these vectors are going to be the same dimension, let's say 20 dimensions. Then I'm going to take the first word's 20-dimensional vector, add it to the second word's 20-dimensional vector, add it to the third word's 20-dimensional vector, and so on. So I'll add up these 5 vectors, maybe a weighted average, maybe just a regular average, and then forget, we lose the word order, and now we have a fixed length vector representing a sentence in some sense. But it does have some semantic information because maybe the word vectors are not just one-hot encoded vectors. Okay, if they were one-hot encoded vectors, this operation is the same as having a bag of words vector at the end of the day. Okay, so it may retain some semantic information if the word embeddings are clever or non-trivial. They do capture some semantic information. And then we have a fixed size input, and then output is just a classification output. Okay, so those two are just teasers for just getting a sense of, hey, this is how we could have, if we had embeddings, we could do something like this. Of course, it is going to lose sequential information. If we don't even have embeddings, we can just use bag of words. Of course, we are losing sequential information. We are not even using any encoding information. Okay, that's the first example. So those are 2 examples. And now let's talk about, yeah.
Could you please repeat the baseline 2 again?
Yeah, I'm just saying that if you had, what is a good sentence? So, okay. We will study NLP. For each one, there'll be a vector, right? So I'm saying that, let's say we have a vector for each word, okay? Whatever the numbers, and then you just add them, divide by 4, let's say. So that's a fixed vector representation for the sentence. Of course, we are losing any order and all that stuff, but as long as encodings are good, you do maintain semantic information about the sentence up to some level, roughly speaking, right? Okay. All I'm saying is, if it just happens to be, let's say, the one-hot encoding representation, then certainly the final thing is just going to be a bag of words, right? It's just going to be the 4 words, and everything else is going to be 0, right?
Yeah. Okay.
Yeah. So that's all I meant.
Okay, got it. Thank you.
Yeah, but as long as if you use somewhat non-trivial encodings here, you can actually do better than baseline 1.
Okay.
Because it does capture some semantic information at least. Not, I wouldn't say better than. I'm just saying that it does capture some semantic information as long as as a starting point you do have some embeddings, and that's what we'll study in 5 minutes.
Okay, got it. Thank you.
So CNN, I am gonna skip this slide because we have seen that just last session. So what is the key idea? So I'm not talking about the first bullet point. We know that CNNs can capture location invariance. For example, where the cat is not very critical, and also there's some compositionality where lower level features get aggregated to higher level patterns. That's fine. So this is something that we've discussed before. So that's not the key thing. What is key from this slide is that what we're going to do is represent the sentence as a matrix. How are you getting a sentence to a matrix, right? First of all, as I said, sentence is a collection of words with some sequential ordering. each word, let's assume we have an encoding. Okay, we have a vector. So very similar to baseline 2. Baseline 2, we said we have a vector for each word. So we're going to have a vector for each word. Okay, and because we have a vector for each word, we're going to represent the sentence as a matrix where the first row will be word 1, second row will be word 2, third row will be word 3, and so on. Okay, so the matrix rows are not, they're not interchangeable. I mean, the second word has to be in the second row, third word has to be in the second, third row, and so on. Okay, so this is how we'll represent a sentence. Okay, to do that, we certainly need the word embedding, right? So word encoding. But you can certainly use a one-hot encoding here. Okay, so you can certainly use like 1000 if you want. That's also fine. But let's say we start with a matrix representation like that. Then the architecture is as shown in this figure. Okay, in this figure, focus on, I guess, focus on the left-hand side. This is that matrix that I was talking about. Okay, this thing here. So the example sentence that we have is, I like this movie very much. Okay, and with an exclamation mark. So each of them has a vector representation. Okay, by the way, vectors doesn't have to be just for words. It can also be for punctuations and other things, right? So other tokens, for example. So I have these words or symbols. For each one, I have a 5-dimensional vector, right? So 5-dimensional vector, d is equal to 5. I've represented the sentence as a matrix. Now what I'll do is apply a convolutional layer, okay, con layer. But this con layer is gonna have, okay, so the input is gonna be is a tensor. It just happens to be a matrix. There's no depth, okay, clearly. Now that's one thing, no depth. No depth. Second thing is the filter width is equal to d. Okay, so what is d? D is just the number of columns of the input matrix. Okay, filter width is d. And then here in the second column here in the figure, I'm showing a bunch of colored patches, right? So there's a yellow patch all the way at the bottom, which is like 2 cross 5, right? So this is 2 cross 5. Similarly, the patch here is also 2 cross 5, and the patch above it is called 3 cross 5. This is 3 cross 5, 4 cross 5, and so on. Okay. So what is 5 there? 5 is just d. Okay, d is equal to 5. Right. Now what I'm saying is these 6 patches in this column here, I'm going to call them filters. Okay. Which means that I need to learn the parameters in those cells, in those in the cells, basically in those matrices. So first of all, remember there's no depth. So which means that when I think of a filter, the filter will just have a width and height, right? So width of the filter, I said I fixed it to be 5. Okay, width I have to decide. The only thing I have to tell you about the filter is how many number of filters. I said number of filters is 6. And what is the height of each filter? I'm going to say, hey, I'll have 2 filters which are height 2, 2 filters which are height 4, 2 filters which are height 3. So I mean, so you can see that, right? So 2 filters which have height 4 rows, 2 filters which have height 3, which means 3 rows, and 2 filters which are height 2, which is 2 rows. Okay. So how are the filters going to work with the input tensor to produce an output tensor, right? So if you take the yellow thing, right? So yellow block, and you want to slide it over the input matrix, you can't really slide left and right because the filter width is the same as the input matrix width, right? So you can only slide up and down. Okay. So you start with the top. Okay. You start with this filter, start with the top, I and like are the first 2 rows. You get the first entry. Okay. And then you slide, with a stride of 1. So you take like and this with the filter, and you get a second entry, and so on. So you get a 5-dimensional vector as an output activation map given the operation of this filter on this input. Okay. Similarly, if you apply this filter, you'll get, actually it should not be 5. 1, 2, 3, 4, 5, 6. Should be 6-dimensional vector here. Okay. Similarly, you got a 6-dimensional vector here. Okay, let me use a different color. 6-dimensional. And similarly, if I apply a 3 height filter, I'll get a 5-dimensional vector. And similarly, if I apply a 4-dimensional filter here, I'll get a 4 height vector. Okay, so those are the filter maps. So what we are seeing here, are the filter output maps. Okay, of course they are of different sizes because these filters happen to have different heights. Okay, they're not the same height filter. And then once we have the filter maps, filter outputs. Okay, then what we can do is apply what is called a max pool operation. Okay, it's called max pool. So it's called one max pool. So what we're going to do is out of these 4 numbers, we'll just pick the highest number. Okay, that number is going to move forward. So in that sense, this step here is the output of the max pool operation. Okay, so each filter produces these intermediate quantities, right? This is the filter outputs, and this part, these are the filter outputs, this and all that. And after you do max pool from each of those vectors, I'll take one number. Okay, one number each. Okay. That's max pool operation. Once I do the max pool operation, I'm just going to concatenate all those max pooled numbers into one vector, and that's my vector. From here, I can just fully connected layer to get the scores. Okay. That's this architecture. Okay. I know I'm doing a little bit faster than usual, but just recap the steps. I have an input matrix. I'm applying filters. Filters I chose their width to be 5 so that I can't do filter sliding left to right, but I can do filter sliding top to down. I have 6 filters. So therefore, they produce 6 activation maps. Those are these 6 long vectors that you're seeing here. Okay, 6 activation maps. For each activation map, I'm going to apply a max pool operation because these activation maps happen to just one dimension. If I apply a one max, it's called a global max pool operation, I just get one number at the end of the day. Okay, so from 4 numbers, I get one number. From 6 numbers, I get one number, and so on. Once I get these max pool outputs, I'm just going to concatenate them. I'm going to get 6 numbers because I have 6 filters. Okay, once I have the 6 numbers, I'm just going to transform them using a fully connected layer into 2 scores. Okay. So that's it. That's a CNN-based sentence classifier. What it is taking advantage of is the sequential information. Okay, so that like is following I, and this is following like is something that the CNN is this model is picking up, right? And the second thing is that this model is dependent on what is the encoding of the words. Okay, and it can be one-hot encoding, but we'll see that we can actually use Word2Vec, more interesting encodings, and that's going to be a nice segue into encoding for the rest of the session. Any questions about this part?
I have a question. Why is 5 here? It's optional, or just it can be 2, 3, or?
Oh, you mean the filter bit?
Yeah.
So it just happened. So yeah, 5 is just an encoding that was chosen a priori. Yeah, this is not specific to the model. So let's say, and you'll see that in Word2Vec, which is a certain type of encoding that, given a word, it will give you a vector basically. For example, this D is going to be 300, for instance. Okay. So if D is 300, then you'll also in this architecture choose the filter width to be the same 300. Okay. So that 5 is just something that is externally chosen.
Yeah, but in this matrix, in the first row, we have it's associated with the word I.
Yeah, there'll be 5 numbers. Of course, there's going to be 5-dimensional vector for the word I. That's that vector. Yeah.
And the numbers are just, they can be anything.
Those numbers are not learned. I mean, here the numbers are input, right? So I'm assuming I already have a vectorial representation for each word.
Okay. So these are not 0 or 1. So yeah. Okay.
No, you can use. So if I chose, let's say my vocabulary size is exactly 7, then I could have a one-hot encoding vector here, which would be instead of D is equal to 5, D could be 7, and then I would be like 1 0 0 0 0 if you want.
Yeah.
But this is something that is external to this architecture. Okay. And in fact, we'll talk about how to get a good bunch of numbers here, and that's going to be the rest of the talk, rest of the session. Yeah.
Okay. Thank you.
Yeah, that I guess the main focus of the session. I know it's a little bit slow here, but the main focus is again to get basically what I would call an embedding. Okay, an embedding is basically takes a word and gives me a vector. So you can just say def, in Python, you can say, hey, get vector, and you can pass a string, like, this, and then it'll say return some vector, okay, some 0.3, 0.2, whatever with the number. It could be, for example, I was just saying earlier, it could be 300 cross 1. If it is, this vector, and if it's some other vector, some other vector, some other string, some other vector, right? So that's all this is. And embedding is basically a mapping from words to vectors, and we have seen one-hot encoding as an example encoding, right? So, but what we want is these vectors such that semantically similar words can be represented similarly, which means that they, for example, can have similar vectors. Okay, and this is the idea behind. We just call it vector space models, but this is not very important. Okay, whether you call them vector space models or not, you just want similar words to have similar vectors. Okay, so in that sense, for example, remember, if you go back to Word2Vec, if you go back to one-hot encoding, there'll be one-hot encoding vector for the word cat, and one-hot encoded vector for the word dog, and one-hot encoded vector for the word aeroplane. Okay, we just saw at the beginning of the lecture that the Euclidean distance, for example, between cat and aeroplane, and dog and aeroplane, and cat and dog is all the same. So it's not like, so cat and dog are not really close to each other. Okay, for example, in terms of similarity, if you just do an inner product or some sort of Euclidean distance or whatever, okay, that's something that we will fix. And one of the ways to fix it is to say that is to assume something, right? So, and that assumption, assume something about what do you mean by words have some similarity between them. Semantic similarity is that, hey, words will have semantic similarity if they appear in the same context multiple times. If for example, with dog, you talk about a vet, and you talk about vaccines, or you talk about pet food or whatever, and you can talk about a cat, and then again vet, vaccines, and food, or pet food. Then the dog and cat appear in similar contexts, and therefore they should have maybe similar vectors. Okay, there are a couple of approaches to get to these word vectors, which can capture semantic similarity. One of them is called count-based. One of them is a count-based model. It's actually just a traditional model. We are not going to spend time on it. And the one highlighted is the one which we're going to talk about. And this is where Word2Vec falls into. Okay, it's a prediction-based approach to get, at the end of the day, vector representations of words. And the words, hopefully, similar words or words which appear in similar contexts should have similar vectors. Similar vectors just means, the number should be almost the same, or if not, the inner product should be high. If not, maybe Euclidean distance should be low. Okay. Yeah. So again, just to recap, what is an embedding? Is just a mapping from each word to a vector. For example, university has some vector, and class has some vector. Okay, that's what an embedding is. So how do we learn this embedding? Okay, how do we get these vectors is the question. And the crux of the idea is the following, right? So the idea is going to be very similar to what we did with gradient descent and learning parameters of the filters, or learning the parameters of the fully connected layer, and all that stuff that we've seen before. Okay, the idea is we'll start with this W, which will have parameters. Clearly, the vector coordinates are going to be the parameters now. We'll just start with some random values for each of the vectors of each of the word, and then change these parameters. Okay, change the coordinates, change these embeddings, such that there's some performance improvement in a meaningful related task. Okay, there's going to be some extra tasks that will say, hey, there's going to be a task. We want to change the embedding vectors. We start with some random numbers for each word's embedding or each word's vector. We start with some random numbers, and we're going to define a task. And then we'll say that each of the entries in this embedding is going to be a parameter now, and we're going to tune these parameters such that on this extra task that we're going to define, we're going to do better in some sense. Okay, that extra task is just going to be a classification task, for instance, and then therefore we want to minimize classification loss. So we're going to change the word vector such that the classification loss is going to be lower, for example. Yeah. So let me define the, so what we're going to discuss now is just an example, is just to motivate, it's a teaser, and we're going to talk about Word2Vec specifically next time because we're running out of time. It's just a way to think about how do I get embeddings, right? How do I get embeddings for words? So what we'll do is talk about what is the task first, and then tie it back together to the idea that we talked about, which is, hey, if I have a task, then I'll start with some random vector representation for each of the word, and then improve those vector representations to do well on the task. Okay. So here's the task. So the task is to classify, it's a binary classification problem, is to classify whether an input sequence of 5 words is valid or not valid. Okay. So I'm going to input 5 words to it's a classifier basically. I'm going to input 5 words, and the output should say whether it's a valid sequence or invalid sequence. Okay, so that's my task I'm trying to construct. A 5-word sequence is just called an n-gram, by the way. It's not. It's just a I guess terminology used in the NLP community. So here's the 5 words example. Operates the largest medical school. That's a valid sequence of 5 words. If we got it from Wikipedia, let's say. Then this is the valid sequence. Okay, we'll just say this is the label for this 5-word sequence, and then we'll arbitrarily change for some for each sequence we'll arbitrarily change, let's say the one of the words. Okay, and then this is going to be an invalid sequence. So we can always generate this data, right? So we can always generate this fake data. I mean, valid sequences we can just get it from some corpus like Wikipedia, and invalid sequences we can just arbitrarily change the word, and most likely it's going to be an invalid sequence. Okay, so now we have this training data, and here's what our model would look like. Okay, so what we want to do is learn the embeddings, the parameters we said, right? So we're going to pass each word through the same embedding function. It'll have the same parameters. It's just for each word it's going to maintain a vector, right? So so for operates there'll be maybe it's a random vector here. Maybe for D there's an initial vector, largest there's an initial vector, and so on. There are all these vectors. And then given those vectors, you can just concatenate them or add them whichever way you want. And from those vectors, you wanna, for example, do a fully connect layer, or any simple classifier you want to pick, you can use. Let's say a fully connected layer, going to 2 scores which are valid and not valid. So you just want to have, if you had right sequences, then you want the valid score to be high. If you had invalid sequences, then you want the invalid score to be high. Okay, and how are you going to learn? There's going to be some parameters for the classifier itself, the fully connected part itself, and there's going to be some parameters in the W, right? So both these parameters are going to be learned. Okay. And although we learn both these parameters, we only care about the parameters inside W. Those are the parameters corresponding to the word vectors. Okay, and this extra task of this classification is something that is just arbitrarily constructed. At the end of the day, we just want this W. Okay, so that's the idea behind getting word embeddings. Yeah, and this is exactly what I said. The task itself is probably not interesting and may not be consequential, but at the end of the day, we'll get a good bunch of parameters in the W. So how do we think of W, right? Think of W as, hey, the word operates. Sorry. Has some, bunch of numbers, okay? And those numbers hopefully are updated so that the classification performance was high. Okay? Similarly, the word something else, largest hospital, let's say largest, it corresponds to some row here, and there will be some numbers here, and those numbers are updated to be the best numbers possible to help in the classification performance. Right, so you can think of W as really a matrix. Rows being every row corresponding to basically a word. Okay, and that's it. So if you do that, you can. And this is basically the idea behind learning good embeddings. And the 2 of the embeddings are called that are somewhat old now, but 5 years old or more. This is how they are learned. Okay, and we'll actually spend some time digging a little bit deeper into what exactly is the classification task that was done for Word2Vec in the next session. But once you learn the W or this matrix, you can always visualize it. And one of the visualization techniques that we've seen from last time is t-SNE, right? So you can just visualize with t-SNE and get a sense of whether the embedding is good or not. So let me pause here because we are running out of time. I wanted to share a different, a different link, which is this visualizing Word2Vec embedding. So forget about Word2Vec. I mean, I'm just saying visualizing that W using t-SNE. Here they actually show you how to visualize the Word2Vec embeddings using t-SNE, okay, using the package that I mentioned, GenSim. So GenSim has a nice way to get these are the Word2Vec, I guess, data, a pre-trained model. I mean, somebody was asking for pre-trained model. You can get the Word2Vec model, and for a bunch of words, you can get get their embeddings, and that's what's happening in this cell. And then this we have already seen last time. You can import t-SNE from sklearn, and you can just ask for t-SNE and then
not
pass
able to see anything.
Oh, wow. I am so sorry. This is not good. Okay, so let me actually share this. I can't do that. Great. Uh, I'll share this, but all I was trying to show was this link where this person has visualized some word embeddings using t-SNE, and I was just saying that, you know, you can load the pre-trained model. That's one cell. Get the embeddings, or this, you know, in this case, 300-dimensional vectors for a bunch of words. Here, there's a bunch of words. And then you can always call t-SNE, and we have seen how to call t-SNE. There's an example in the examples folder in our repository. So you can just always call t-SNE here, and that's it. And the next cell is plotting them. So this actually is a plot of a bunch of words in using the Word2Vec vector representation. Okay, Word2Vec embeddings. So we'll revisit this anyway next time, but I just wanted to show you, and let me share the link and stop sharing because I'm not able to see this chat. For some reason, I think they Zoom updated, and you know, some things are a little bit different now. But this is a link to the notebook. Just focus on the first 4 cells. It's just saying load the word vectors, get the word vectors for a bunch of words, and then plot them, basically. And then get the t-SNE instantiated and then plot the 2-dimensional vectors. Okay. So we'll resume back and talk about Word2Vec in a little bit more detail to get a sense of how are these words, how are we getting these vectors next time, early part of next time. And then jump over to capturing sequential information. Those are the 2 things, right? One is getting good embeddings of words. With that, we have good embeddings for images and words. So therefore, at least we have nice numerical representations for words and images. Next, we can talk about how to capture sequential information. Very similar to time series analysis. We have temporal information, we want to exploit it. And we'll see some of the models there, which are basically called recurrent neural networks, LSTMs, and all that stuff. So that's going to be next session. So with that, let me pause here. I'm going to stop the recording, and folks who have questions, anything that we discussed today or even the previous sessions, you can stay back and ask me. Thank you.
Professor, can you go over the word embeddings again, like how we are producing that? I really did not understand steps.
Yeah, so I will definitely go over that. Folks who want to leave can go ahead. But so your question is about how are we getting word embeddings? Is it?
Yes.
So we're going to look at Word2Vec next time. So let me just share my screen at the moment. Yeah. Can you see my screen?
Yes, I can see, Professor.
Okay, that's good. So let's see. I can't see the. Okay. I think I might have closed. Okay, give me 1 second. I thought I'll share the. Okay, let me share my annotation so that it's easier.
Professor?
Yeah.
Before you start with that, like, me and Shruti, we wanted to talk about our project ideas with you. Can we stay back till after everyone is done to talk it out with you?
Yeah. Okay, so yeah, definitely. I didn't stop the recording, by the way, just so you guys know. Yeah, definitely. Yeah. I just want to finish this piece, just a recap of embeddings again,
Sure.
and then I'll stop recording and certainly stay back, all the way to the end, and we can discuss stuff. So
Thank you.
the question is about how do we get um, the embeddings, right? So let's go back here. Learning and embedding. So let's start from here. This is just a recap. By the way, if you have a specific question, just let me know now. If not, I'm going to recap this.
Yeah, I would like to go for a recap. Thank you.
Yeah. So what I'm saying is we want to learn W, okay? And W is just, I just literally wrote it here. W is just a mapping. It's just a function, which is given a word, give me a vector, right? Okay. So for every word, it has to maintain a vector, right? And that vector, I'm saying, the vector for every word, just start with some random numbers in those vectors. Okay, so let's say I have 10 words in my vocabulary. Each of the words will have a vector corresponding to it, and those vectors I'm just going to start with random numbers. Okay, the coordinates of the vectors, right? Okay. So each vector will have a bunch of random numbers in there.
Dimension of the vector?
Yeah, that I need to choose. So I'll choose something like 300 or 5 or 20 or whatever choice.
Okay.
Yeah, I need to choose that. So therefore, if I have 10 words in my vocabulary, then for each of the words, I have let's say a 5-dimensional vector. Okay, that means there are 5 numbers that I need to tune for each of the 10 words in W.
Okay.
So I need to tune 5 numbers. I need to tune 5 numbers for each of the 10 words. Okay, so 10 is the vocab size. VO vocab size, and 5 is the dimension. So I need to tune them. And how am I going to tune them? I'm going to think of them as just parameters. Okay. I'm just going to tune them just like I tune any other parts of my architecture. Okay, any other parts of my model, right? So I will always take the loss, take the gradient of the loss with respect to the parameters, and update the parameters. So, and how do I do that? For that, I need an extra task, right? And the task is what I said. Let's go back to this picture. The task was, if I give a valid sequence of words, then the words will get changed to vectors here, right? If they pass through W, I mean, the W may not have vectors at the moment, but they are, there are some vectors there, right? So current parameters. I'll get some vectors here. For example, I can concatenate them. For example, there's 5 words, and let's say each vector is 5-dimensional. Then 5 times 5, 25-dimensional vector I'll get, concatenating each one of them. So from 25 dimensions, I can go down to, for example, 2 dimensions. I can just do this is like literally a linear transformation, right? Wx plus p.
Okay.
Right. And then, and once I know, once I do the transformation, I'll see what the score is, and I can compute the loss function, loss value. I can do this loss computation over each of my training examples. Each of my training examples is a valid sequence or invalid sequence, right?
Okay.
And when I do that loss, I can say, hey, gradient of the loss with respect to the parameters in this guy. Okay. What are the parameters in this guy? The elements of the vectors, the coordinates of the vectors, coordinates of each of the 10 vectors that I have.
Okay.
Which is those whatever 10 vectors, each is 5 numbers, 50 numbers basically.
Okay.
Yeah. So I'm going to update those 50 numbers, and then I'm going to keep repeating this again and again.
Okay. So till when will you keep doing this? Because this is just the data preparation thing part, right? So
no, this is literally learning the parameters. I said learn. So it's data preparation in the sense that my objective is just learn the embeddings.
Embeddings, which you will be using it for any other model that we are trying to build.
Once let's say there's some training loss which tapers off and which doesn't improve, or I can keep a score of validation score and it doesn't improve, and that's where I'll stop these gradient updates. Okay, from epoch. It's very similar to what you've done in assignment 1 or even assignment 2.
Okay.
I'll stop it, and once I stop it, I'll forget about this task because this task was itself inconsequential. I'll just remember dump for each vector each word whatever vector I finally got, starting from the random initialization I did, those vectors I'll just dump to disk.
Okay.
Those are the ones I'll reuse elsewhere. Those are the ones I can reuse for these, for example, CNN model.
For what?
For the CNN model,
Okay,
like
CNN
for
model.
example,
Yeah.
I mean, doesn't have to be just that, like we just did that here. Yeah, I can use those vectors here. I can use the vector any other place. Yeah, many places. Wherever you use bag of words or wherever you use one-hot encoding, you can do that.
Okay. Oh, this is interesting. Thank you, Professor.
Yeah, we'll recollect. So for the rest of the class, we'll kind of redo this anyway with Word2Vec a little bit more specifically for the specific tasks that were used in Word2Vec paper from 10 years ago. So it will become more clear. Yeah.
Professor, once you stop the recording, I have a question regarding ResNet.
I'm stopping now. This just for folks so that they see it. Okay, thanks. So let's stop it.